So now that we've got our discussion of Java memory model semantics out of the way, let's turn our attention to something a bit more practical, which is an overview of synchronizers that exist in Java. And we're going to talk about a bunch of different kinds of synchronizers, and you'll understand why I have these funny symbols here, like passing a baton and some flags from a train crossing and a car accident. You'll learn in a second why we have all those different symbols, because they're meant to help to give you an intuitive understanding of different types of Java synchronizers. So what is a Java synchronizer? A Java synchronizer is an object, typically an object that's shared between multiple threads in a process, that is used to control the flow of cooperating threads based on the state of the synchronizer. So if you take a look at synchronization in computer science, you'll see a whole bunch of examples that are illustrative of what we're about to talk about. Some classic examples of these things, we'll talk about this a bit more when we talk about semaphores, but things, for example, like trying to share a railroad track with multiple trains is a good example of synchronization. You really don't want two trains on the same track at the same time, especially if they're going towards each other, because chaos and insanity will result. Java synchronizers are used by threads to ensure that their interactions obey certain properties. So we want the threads to behave nicely. Probably the most important thing that you want threads to do is not corrupt shared mutable state. And if you take a look at the link at the bottom of the page, you'll learn why shared mutable state is the root of all evil in concurrent programs. And of course, that's correct, but it's also just a natural side effect of concurrent programming often. So we have to learn to live with it. And therefore, we have to understand Java synchronizers in order to mitigate that potential evil. So here's an example of shared mutable state that will get you in big trouble. So we have a class called non-atomic ops, and we have a field called mCounter, which we set initially to 0. And then we're going to go ahead and have two threads, thread T1 and T2, and thread T1 is going to call the increment method, and thread T2 is going to call the decrement method at the same time. And of course, the interesting question is, what will the results be? And the answer is, who the heck knows? Because the increment and decrement of mCounter is actually not atomic, because it actually involves multiple steps. It involves loading the value of mCounter from memory, incrementing it, and then writing it back to memory. And if you have two threads of control at the same time that are working off the same unsynchronized, mutable shared state, or in this case, mutable shared field, then chaos and insanity will result, and who the heck knows what the results will be. So there's various ways to solve this problem. One way to do it is to use the synchronized keyword, which is part of the Java language itself. And you can see here that we're going to kind of take a very coarse-grained solution where we're going to put the synchronized keyword on each of the methods. So the increment method will have a synchronized keyword saying it's a synchronized method. The decrement method will have a synchronized keyword. It says it's a synchronized method. And what that means, when thread T1 runs or thread T2, whichever one gets there first, they will have exclusive access to that critical section, which basically is the scope of the entire method. So in this particular case, we're going to get correctly synchronized output, but at a very coarse-grained level. So this thing will basically, in this particular case, it's going to starve out, whichever thread gets there first will starve out the other thread, because it's just going to keep executing forever, incrementing the counter until it wraps around. So while this will in fact not have corrupted data, whereas this version will have corrupted data, it's also not particularly useful because it locks the other thread out for forever, which is not really what we want. So a more fine-grained way of doing things is to use a synchronized statement instead of a synchronized method. So you can see here that this was the synchronized method. This is a synchronized statement. And so what's going to happen here is we're going to synchronize just the incrementing and decrementing of mCounter. And so what'll happen there is this, again, will still run forever, but those threads will basically synchronize each time through the for loop, and therefore roughly take turns. They may not go alternating in lockstep, but one thread will get to run for a little while and it'll increment counter atomically, and then the other thread will get to run for a while, and it'll get the chance to increment or decrement the counter atomically. And we never have to worry about M counter actually being corrupted, because two threads will not be reading and writing to it at the same time. So again, it's not a very useful program, but the point is that we won't have to worry about the state of M counter ever being inconsistent. It'll always be a consistent value, whatever it happens to be when it's incremented or decremented atomically. And again, this is very important, because if you don't put the synchronized statements in there, then counter is just a good old integer, and it'll end up being cached in each of the threads as it's incremented or decremented. And it's very inconsistent when the caches will be updated and how the information will be pushed through the memory hierarchy. Now, one of the consequences of the synchronized keyword, and we'll talk about this later when we talk in more detail about built-in monitor objects in Java, is that in addition to synchronizing the state and only allowing one thread in that critical section at a time, it also has the side effect of pushing the data from one thread's cache back up to the shared memory part, which is the field M counter, such that when another thread reads, it'll get the latest and greatest version. And so synchronized has a couple of different behaviors in Java. It deals with cache management and flushing and reading of data from caches, and it also ensures that only one thread at a time is in the critical section that's accessing shared mutable state. Some other things you can do with synchronizers in Java is ensure that threads will run in the right order, at the right time, and under the right conditions. And that turns out to be a little different from not corrupting shared mutable state. Not corrupting shared mutable state is a mutual exclusion property, whereas this discussion we're about to have here is more about coordination. And that's why I use the metaphor of passing a baton. You have to coordinate between the two parties to make sure you don't drop the baton. So there's some examples which we'll take a look at later. This is an example of something called ping pong wrong. And what ping pong wrong does is it goes ahead and will have two threads that are supposed to take turns saying ping and pong and alternate. But in this particular case, one of the threads just runs to completion, and then the other thread gets to run. And that's because there's no coordination between the threads. That's why it's ping pong wrong, because it's not coordinated properly. There's also a synchronized version that does, in fact, coordinate the threads properly. And we'll take a look at those later as well, and I'll demonstrate how to use them. And they, as you can see, if you look carefully at the output, it says ping, pong, and each thread alternates doing ping and pong. So it's all nicely coordinated and runs in the right order at the right time and so on. So let's talk a little bit about how common synchronizers are in Java. So the first thing to be aware of is there's actually synchronizers defined at multiple layers in the Java platform. And this applies to Android as well, which is just another variant in some sense of the Java platform. So the Java language itself contains some features that synchronize threads, in particular things like volatile variables that we'll talk about later, and built-in monitor objects in the form of these synchronized keywords like synchronized methods or synchronized statements. So that's one level. The Java virtual machine or the Android runtime has it built into the Java language. Then there's also a whole pile of other synchronizers that are provided as part of the Java class library layer, which is atop the Java execution environment. And these include things like Java atomics, Java locks like reentrant lock or reentrant read-write lock, and other synchronizers like semaphore, condition object, stamped lock. There's various other classes that implement synchronization in different ways. There's also a slew of barrier synchronizers as well. In this class, we're going to focus pretty evenly on synchronization mechanisms and Java threading mechanisms. It's roughly about the same amount of coverage. And in fact, for each of the programming assignments, you'll see that part A will always focus on the threading parts, and then part B will always focus on the synchronization parts. And so it'll give us a chance to experiment with a bunch of different threading mechanisms and a bunch of different synchronization mechanisms. And we'll keep going each time. We'll add some new stuff, and then we'll do some other stuff. And that way, by the time you're done, you will have had a chance to use almost all the different threading and synchronization mechanisms that are part of Java. Synchronization is complicated, and the reason why it's complicated is it requires coordinating the interaction of two or more threads that run concurrently. And so if you're not careful, you can have all kinds of complexities that'll creep in, and we've outlined a few of those before, things like deadlock, for example, and other kinds of hazards that can arise. But basically, this is all because things are trying to share a common space, a common memory space, a common interaction space. And so we have to make sure that they're properly coordinated and properly synchronized. Now, it turns out that there's other ways of solving these kinds of problems altogether. We're not going to focus on this much in this course, but if you were to take a look at Java's parallelism frameworks, like the fork join framework, or the parallel streams framework, or the completable futures framework, or the more modern reactive streams frameworks that are part of modern Java, you'll see that they often solve the problem by partitioning the space of processing in such a way there is no sharing of state. And that's another way to solve the problem. So you can address the need for synchronization by just not sharing anything. And that's another kind of turn of the crank, or another bite at the apple, if you will. We're not going to focus on this much, but be aware that this concept of dividing and conquering the data space to partition it to avoid sharing is another time-honored way of being able to have things run and scale more effectively, especially on modern multi-core processors. So that's the end of our overview of Java synchronizers. At this point, you really don't know enough to be able to do assignment 1B, which deals with some synchronizers. But by the time we get through the other material, you'll be ready to do assignment 1B, which I'll be releasing here very shortly.